This is section 17, definite integrals graphically, example 1. So, we found Riemann sums, areas under the curve, right? We found exact area using limits. Now, we're again going to find exact areas, but instead of it being with limits, it's going to be with the graph itself. And when we do that, all of the graphs that we're going to be looking at today are going to be simple functions, simple piecewise functions. So you can have a linear function or a semicircle, which we know how to find the area of, or something of that nature. So it'll be very simple to find the area under the curve. But we need to talk about the notation for this. The notation for this is a definite integral notation, and it's what you see here on the screen. Okay? We define the area between the function f of x, the x-axis, and the lines x equals a and x equals b as the definite integral. And this is how we write it. Okay, you have a very skinny s from a to b of f of x dx. The f of x thing is the integrand. Okay, it's typically the equation or the function that you're integrating. The dx tells you what you're integrating with respect to. And it's very important that you include this because later on in your calculus career, you might have to take double or triple integrals, in which case that letter would be very, very important. You have the integral sign, and then a and b are your lower and upper limits of integration. And so it tells you what you're going from and then what you're going to as far as that area. Now, the reason that we have this equation goes back to our Riemann sums. So we know that we're finding the area under the curve by taking a bunch of rectangles and adding them up, right? And when you take the area of a rectangle, it's base times height. The base is dx, so it's delta x. It's that little change in x. And remember from the last section, we're trying to make that infinitesimally small so that we can get the best representation of this area under the curve as possible. And then f of x is the height. So it's just base times height. And then the s, the actual integral symbol is an s because we're summing it up. Okay, so it's a summation of adding up all of those itty-bitty rectangles. Now, when you find the area under the curve, you should normally think that an area is always positive. But an integral can be positive or negative. So when you find an integral from left to right, so if a is less than b, if you're finding it, say, from 0 to 2, right, that's left to right on a number line, you're doing it the correct way, quote unquote, right? So the correct way, like that says. Okay, and when you find it the correct way above the x-axis, it's positive. If you find it the wrong way, so let's say instead of going from 0 to 2, we went from 2 to 0, that's going left on the x-axis. Well, that's the, quote, wrong way, which means that your area would actually be negative. Also, when you're underneath the x-axis, it switches the sign of whatever it would be if it were above the x-axis. So a positive area is going to be above the x-axis, going the right direction. A negative area is going to be below the x-axis, going the right direction. Okay, because when we find those areas, we're going to take the top and then subtract the bottom. So it's very important to know all that, and I'm going to go over lots of examples where we actually use these properties. Okay, and it's all summed up in this table right here. And you can think of it as left to right is a positive value, right to left is a negative, above the x-axis is positive, and below the x-axis is negative. So depending on which combination of that you have, that determines the sign of your actual area. And again, it's much simpler to just see. But there are a couple of rules that we have to keep in mind if you have to find the integral as an area, and we will because that's what this section is about. First, if you go from a number to itself, okay, that's essentially just the line that's there, right? Or potentially a line, possibly a point. And the area under a point, if it has no x dimension, is just 0, right? Because it didn't move. There's no base. The base is 0. And 0 times anything is still 0. if you want to go backwards, so if you have to go from A to B, but you actually want to flip it, then it would be the negative version, right? Which makes sense because negative's going the wrong way. So if you want to flip the integration, your limits, then you would just do the negative. You can multiply by a constant, you can add, and you can subtract, and you can actually add pieces to get a whole piece, right, to get a total. So let's go ahead and do this. Now, as we're doing all of this stuff, we are going to pay attention to the actual area, so it's going to take a minute to do this example. First, A is going from 4 to 4 of this function, and all these problems are dealing with this function that we see on the screen. So if I'm going from 4 to 4, the answer is just 0, because that's essentially that line right there, right? Because that's 4, no area. There's no area there, right? It's a line. A line doesn't have area. From 0 to 1, that would be from here to here. 0 to 1. Okay, so to find that area, it would be base times height, which is just 2. So that's 2. Now, when you do problems like this, I highly suggest you actually fill in the area, because then when we get to later problems, you can still refer back to it. All right, now it says from 1 to 3 for part C. So that's base times height, so that's 2 times 2 divided by 2 because it's a triangle, which is 2. So that is also 2. So to get from 0 to 3, I would add 0 to 1 and 1 to 3. So 2 plus 2, which is 4. Now I have from 3 to 6. Now keep in mind, this is an area under the curve. Under the x-axis, which means it's negative. And it would be base times height, so 3 times 1 divided by 2, so 3 over 2. So that's a negative 3/2 area. Now to go from 6 to 3, I'm taking that and I'm reversing it. So because I'm flipping my limits of integration, whatever sign it was, I'm doing the opposite of. And so that makes it positive 3 over 2. Now I'm finding 0 to 6 for part G. So I already have 0 to 3, and I have 3 to 6, so I can add them together to get the total area. So 4 minus 3/2 is 5/2. From 6 to 10, we've got to look at our graph again. This is a semicircle with a radius of 2. So remember, it's pi r squared. Our radius is 2. And then it's divided by 2 because it's only a semicircle. So this is going to be 2 pi. From 10 to 6, that's going the wrong way, so it's going to be the negative version of that. And then from 0 to 10 would be adding 5/2 and 2 pi. So because 0 to 6 is 5/2 and 6 to 10 is 2 pi. So that is just 2 pi plus 5/2. Don't worry about adding those. Do not worry about adding those. Now for the 0 to 10, I'm going to take both of those and do the opposite sign. So it's going to be negative 5/2 minus 2 pi. All right, now we're going to the other side. We have from negative 1 to 0. That is in the correct order because it's negative to positive, right, least to greatest. So we're only talking about this section right here. So it's base times height 1 plus height 2, right? So 1 plus 2 plus 4. 1 times 2 plus 4, which is 6. So that area is 6. Now we are going from negative 3 to 0. So we need to find this area here. So I'm going to, let's do this area, and then the other one, the middle, and then the left. So we have 1, a base of 1, and then a height of 4 and 6. Oh, wait. We have to divide by 2. That's 3. Because it's 1/2 times base times height 1 plus height 2. That's 3. Okay, sorry. So for this middle area, we have 4 plus 6, which is 10, divided by 2, which is 5. And then for this triangle, we have 1 times 6, which is 6, divided by 2, which is 3. So that whole area would be from -3 to 0, 11. And then from 0 to -3 would be -11, right? Wrong way. -3 to -4, well, that's this area here. It's negative, and it is 1 times 1 divided by 2, so -1/2. So -4 to 0 would be +11 minus 1/2, which if you simplify gives you 21/2. And then -4 to 10 is P and J. Right, so if I have 2 pi plus 5/2 plus 21/2, and I put it all together, we get 13 plus 2 pi. Now, R is asking for the absolute value of that value. Okay, and the absolute value of that happens to be the same thing, 13 plus 2 pi. Now look at S. S is talking about the absolute value of our function, which means that we're actually going to take the absolute value of every y value you see on this graph, and we're going to change it. So everything that's above the x-axis stays above the x-axis, but everything below moves up, which means that this is actually 1/2 now, and this is +3/2. So we need to take what we had already, our 11 plus 4 plus 2 pi, and add 2. And when we do, we get 17 plus 2 pi. Then from 1 to -1, first, 1 to -1 is going from right to left. So if I want to reverse it, I'm going to take the negative. But there's a negative in the problem, which means it just becomes 2 times whatever f of x would have been, going the correct way. All right, and we're going from 1 to -1 to 1, so 3 plus 2, because we're going from here to here. So it is 2 times 5, which is 10.